recording. Okay, thank you. Our presenter tonight, this is his third time making a presentation to this organization this year. And his first talk will be about meteors after midnight. Why do we see more meteors after midnight? I don't know, but he's going to tell us, okay? And the second part of his talk is, I don't know if anybody's been watching National Geographic Channel. They've had a program on genius. And it just so happened in this program, they mentioned the guy he's going to be talking about here, Sir Arthur Stanley Eddington. And he's going to be doing his second part of his presentation on the Eddington Limit, radiation pressure in the star's atmosphere. And without further ado, Mr. Dave Bailey.
Well, as you can see, I've actually got 4 presentations. However, this one is not ready. However, I'd like to get an idea of interest. I'm going to point at each one of the 4, and you can raise your hands if you think it would be interesting, or wave your hand like this, meaning no. First one, air friction vaporizes a meteor, question mark.
What is pro and what is con? Thumbs up or thumbs down?
Wave your hand violently if it's no. Otherwise, that's yes.
Okay.
Okay. Evening meteors cannot catch up to the Earth. Question mark.
I didn't vote on the first one, actually.
Oh, okay. Let's look at this again. Air friction vaporizes a meteor. Question mark. Some interest. Yeah. Evening meteors cannot catch up to the Earth. Question mark. A little bit less interest. Okay, I'll probably do this one first. It's the shortest of the 4. Eddington Limit and Opacity. Yeah, okay, this one scores better. And what if a planet crashed into the sun? Some interest, but I'm not ready because I haven't run the math.
You should hook up with Scott over there.
I think if you crash Saturn into the sun, it would probably destroy all life on Earth. That's my bottom line. You could not crash Jupiter into the sun because in order to reduce Jupiter's angular momentum to 0, I think would require more energy, more kinetic energy to be expended than there is in the entire solar system. Oh. But I think you could crash Saturn into the sun. Oh. So that gives you an idea of the extent that I've worked on this one. So, 1, 2, 3. And I'll erase this one to make room on the board. Okay. I used to do this for other clubs. I'd put like 7 talks. And then the one that won, I would say, okay, I got to download. Okay. So, the Eddington Limit. Well, we've already heard a bit about Sir Arthur Stanley Eddington. If I can find the right age even. There we go. 1882 to 1944. And as was mentioned, we saw him very briefly, at least I did, in one of the episodes on the life of Albert Einstein. Eddington was the first stellar astrophysicist to give an even approximate estimate of how hot the centers of stars must be. Gentlemen over there might want to use these comments as the core for a much more adequate discussion of Eddington. Arguably, Eddington might have been the first stellar astrophysicist, period. Working without computers, of course, he studied stellar atmospheres using carefully thought out approximations. Thus, an observer in a vehicle hovering just below the surface of the sun would see above him a sky of uniform brightness, a somewhat fuzzy horizon, and below him a hell, again, of uniform brightness. Severe approximation. but you're running without a computer. The words sky, horizon, and hell are my words, not Eddington. He might have used the words, I don't know. It's rather obvious. You call something bright below you a hell. The extra brightness of hell is exactly equal to the sun's observed surface brightness as seen from Earth. As you descend deeper into the sun, both sky and hell get dramatically brighter, but the brightness difference always stays the same. With this, quote, Eddington approximation, that's what it's called, the Eddington approximation and similar mathematical gimmicks, he could use algebra and calculus instead of brute force computer and number crunching. Another example, the, quote, Eddington-Barbier relation states that the, quote, location of the sun's photosphere is precisely at the layer where the optical depth tau equals 2/3. Many of you may never have heard of the optical depth tau, but it's interesting. He was the first person to come up with that number of 2/3, which everybody has adopted. That's where the photosphere is. Basically, it means that if you fired a powerful laser down into the sun, a laser is so bright that the sun's light is negligible. Then, and you monitored how bright that laser was at various depths down. When the sensor that said that it was 2/3 as bright as full brightness, that's where the sun's photosphere is. The third example, the, quote, Eddington Standard Model of stellar structure, which I think dates back to about 1925. He will know. He'll look it up. Give me the date. Right, Ken?
Right. Which one? 19?
I think maybe 1925 for the, quote, Eddington Standard Model.
I would say 19, yeah, close to that anyway.
Yeah. It describes the density and temperature of main sequence stars surprisingly well, considering that Eddington knew nothing about either convective energy transport or nuclear energy production.
So what's a main sequence star, Dave, for the benefit of people who aren't?
A star like the Sun, like Alpha Centauri C, Proxima Centauri, like...
So fairly young and healthy star.
Still burning hydrogen to helium.
Burning hydrogen to helium. Yeah, well, the red dwarfs, some of them are as old as the universe, but red dwarfs tend to have an expected lifespan of like 100 to 1,000 times the length of the universe, the current age of the universe. So they are, in a sense, they're extremely young because they burn less than 0.5% of their hydrogen in their cores. But on the other hand, a lot of them are incredibly old because they're almost as old as the universe. They cheat though. Since they are convective throughout the entire body of the star, all of the hydrogen is available to be burned. Whereas the sun can only burn the hydrogen in the very center part of the core before it starts to say, hey, I'm running out of hydrogen, what do I do now? When there's huge amounts of hydrogen in the outer layers of the star, of the sun. Basically, main sequence stars are, quote, typical stars, not a red giant, not a white dwarf, and so on. Today we're looking at the Eddington Limit, which tells how bright a star can get without quickly blowing off its outer layers. It's a question of radiation pressure, which tends to push the layers outwards, versus gravity, which tends to pull the layers inwards. The Eddington Limit also tells us how rapidly material can fall onto a central mass, such as a star. If you try to pile massive stuff onto a star too fast, the the energy released by the kinetic energy of the infall rapidly makes the star very luminous. It eventually violates the Eddington limit, and it says, no more! And the material that then is falling into the star is slowed down, stopped, and actually repelled back out. It's a similar process. The question is, which is more important, radiation pressure or gravity?
Well, that's similar to your plutonium bomb, when you crush the core down to from about 3.5 inches to about an
Eventually,
inch.
the plutonium says, enough already, I'm going to explode. And the star essentially has said the same thing.
Yeah.
The physics is totally different, but the appearance,
Yeah.
it looks sort of similar. In these talks, in one of them, I'll compare a tiny, tiny meteor to a nuclear bomb fireball. Interesting. They are actually comparable. Okay.
David, I'm gonna throw up something. Go ahead.
Oh, okay. I'll keep on going, but I shouldn't be surprised if something
Throw
happens.
something up on the concept.
In solar units,
There it is. There you go.
solar units means, oh, what have we got here?
That's
Oh,
the, that's the
It's right there.
okay. Can we kill the light?
It's right there, Andrew.
Pull down the screen.
Okay, yeah. Although the screen isn't that bad. Okay.
Whiteboard works as well as the
Yes.
screen, honestly.
Okay, this is called the Hertzsprung-Russell diagram. Across the bottom, this says color, but actually it's temperature. The physicists use variables, and observers use observer variables. The observers thinking they're looking at the color of a star. No, they're not. They're really going to look at the temperature of the star, the surface temperature. Here we've got luminosity. Oh, here, this is the physicist's thing. Luminosity means how bright it is. This is a solar unit here. One means a star that's as bright as the sun. This is the main sequence, and it really does have some wiggles here. And the sun is right about here. And color, I don't know offhand what the color index of the sun is, but anyway, it's right about there.
Well, it's probably about 6,000. You look at the top.
Oh, there's color, yeah. 5777. I rounded off.
Yeah.
Like most people round off to zeros, I round off to repeated digits. So 5777 is an easy number to remember, and it's just about right. So right about there is 5777, and that's the, what's happening? Oh, I don't need this tough stuff on the top, but there we go. Right around here is the sun. This is the main sequence. Here are blue giants, blue supergiants. Sirius is somewhere around here, and Sun is somewhere around here. Alpha Centauri is way down here. Brown dwarfs are down here. Some people say, no, brown dwarfs aren't stars because they're not fusing hydrogen, but some of them are fusing deuterium, which is sort of like the same thing. So I guess we can go back and proceed. And by the way, this is consistent with my policy. I like people to ask questions in real time. The reason why I like questions in real time is because if I told you to wait until the end of the presentation, by the time the end came, you would have forgotten what your question was. So yeah, please interrupt with questions. Okay, in solar units, the Eddington limit is, and I'll show it in two ways. L, oh good, we just lost our blue. Let's try a red. If we lose everything, I'll just have to talk. But I seem to be capable of doing that. L, for luminosity, equals 4 pi C G M over, that one's worse, over kappa P. Okay. Or L over M equals 4 pi C G over kappa P. There we go. Solar units means that here in the case of L over M, the luminosity of the sun is 1. Luminosity, the mass of the sun is 1. And c is the velocity of light. G is the universal constant of gravitation. It tells how strong the gravitational force is. Kappa sub P is the opacity at the photosphere. We'll talk about that later. Opacity is sometimes a little bit hard to get your brain around at first. I'll try to make it easier for you to understand what astronomers are talking about when they say opacity. Basically, it's a different spelling of opaqueness. It's the inverse of transparency. Okay, so here is, this tells what the Eddington limit is in terms of luminosity for a star of mass m, which in the case of the sun means mass of, quote, 1. And this is the main other variable, which is the opacity of the material at the photosphere. And when you do these numbers, you know, plug in this stuff and say, what is the Eddington luminosity for the sun? Well, we don't have to worry too much because this Eddington luminosity of the sun is 38,000. The real luminosity of the sun is 1. Solar units, right? Everything is 1 that relates to the sun. That means that if the sun got to be 38,000 times brighter, the outer layers would blow off into space right away. None of this solar wind nonsense. Solar wind is totally trivial. It's a hydrogen atom here, and then another hydrogen atom here. We're talking about the whole outer layer of the sun going off into space now. Well, it's a good thing. We're safe by a factor of 38,000. However, some other stars aren't like the sun. A star that, a massive blue supergiant with a luminosity of 1.1 million and a mass of 70. You do that division and you get an L over M value of 15,700, which is rather close to 38,000. It's only short by a factor of 2.5. So this massive blue supergiant star, it's sitting at 40% of its critical luminosity. Here's the number. If such a star got 2.44 times brighter, it would violate the limit and begin to lose its outer layers. In actuality, that's an oversimplification because there's two variables here. One is the ratio of luminosity to mass. The other is the opacity of the material at the photosphere of the star. And this incredibly hot, incredibly massive, well, 70 times the mass of the sun, this blue supergiant has a different value of opacity at its photosphere. The material of this photosphere of this star is much more transparent than the material at the photosphere of the sun. That means most of the light pressure just goes right through it because it's transparent. If you painted the sun with black paint, and then the paint would have to be high temperature paint, otherwise it would boil instantly. But if it was 100% reflective, then it would be that much closer to that layer expanding out. So this number, the opacity at the photosphere, is critical. Okay, I'm going to have to stop reading.
So if the sun has that much of a margin before it would even begin to approach
Yes,
this critical.
yes.
Where do you
What
see
have we
this? Where has this actually been observed happening?
There haven't been any clear-cut examples of stars that are past the limit. At least not, quote, normal stars that can be observed. You can't plan an observing program to watch them. But if you're thinking about supernovas, if you're thinking of classical novas, if you're thinking of a few other things, then yeah, there are examples. There's examples of material falling onto a star where the flow, the inward flow seems to be limited, and when you do the math, you discover, oh, well, of course it's limited. It's sitting at Eddington's limit. The material is flowing down onto the star as fast as it can. If it flowed faster, the star would get brighter, and the material would stop falling temporarily, and then would start again when the limit was no longer infringed upon. So I would like to talk about opacity. There's several kinds of opacity, and I'll draw some diagrams. One of them is electron scattering. If you've got material that has a lot of free electrons, here's a bunch of free electrons, and then here's some photons coming in. Photon hits an electron, the electron bounces off. Oh, I can't draw an arrow, I don't have enough. Here we go. And the photon continues. It bounced off the electron. Did you destroy a photon? No, you did not. You scattered it. If you got a bunch of photons coming up from the core of a star, we're sitting right at the photosphere here. Most of the photons are coming upwards. Occasional photons coming downwards, but most of them are coming upwards. When they get scattered in all directions, then that, in effect, cancels some of the upwards directed momentum of the upward directed photons. So even though you didn't destroy a single photon, you scattered them from being mostly upwards to going out in all directions. That means that this material, at least the electrons in the material, get pushed upwards. There's an upwards force. So this is the radiation pressure. So that's electron scattering. I don't really dare write with this thing because it's already fading. Then we've got, I can draw an energy level diagram. This might be hydrogen, and this is zero energy. And here is an electron in hydrogen, which is in this lowest energy state. Actually, it's two states down here because, as we know, there's two energy levels, and they're separated by the energy of a 21 centimeter radio wave. But essentially, these are the same levels here. Photon can come along here. Here's a photon coming. Hits this electron, bounces the electron up into that energy level. What happened to the photon? It's gone. And this is Lyman alpha absorption. Lyman alpha. That's at a wavelength of 1215 angstroms, well out into the ultraviolet. Cannot be observed from Earth. Got to either put balloons into really high altitude, or you've got to, oh, I'm off the edge, sorry. Or you observe from space. Lyman alpha is very interesting, and only since 1957 have people been able to observe it. Okay, here's another transition from, this is the second energy level, this is hydrogen.
And again, these are factors in opacity?
Yeah. Any process that destroys photons in a beam of light means that light beam is getting dimmer. What happened to the energy? It got absorbed by the gas that the photons are passing through. This one, the electron is knocked from the second level up to the third level. This is H alpha, which solar astronomers make use of greatly. This is called bound.
What's it called?
Bound transitions. Because this is a bound state, the electron is stuck to the proton, can't get away. This is a bound state, this is a bound state. Now let's look at a bound-free transition. Here's an electron in the second state, say. Although it's more likely to happen with the first state because most of the electrons in almost all astrophysical situations are down in their bottom state. A photon comes along and knocks this electron up to this energy up here. Doesn't want me to draw that line. This is a bound-free transition. Let me try this other one.
Might have it.
Bound-free. This electron has enough energy so that it's beyond all of these states, and it's now escaping from its former nucleus, the hydrogen atom nucleus. Then another one is free transition. We already discussed that one, where the electron scattering thing.
And all those factor into the denominator of your equation.
They do. And this one is actually let me see, 1 kappa, 2, 3, 4, yeah, free. Yeah, we had already discussed that one. The fourth one that people talk about is negative hydrogen ions. Do I want to go there?
No,
I got something there for you.
What time is it?
it's 9:06.
Okay, we're cool. We're cool.
Look at that,
We're cool.
look what I got there.
Bound, okay, that's cool. That's cool, bound free, that's cool, free. Do we have another category down there? No, okay, all right, well, that's enough for that then. The other category is, involves negative hydrogen ions. What is a negative hydrogen ion? Well, the old, we've lost our, I think the board is slightly greasy. Here's a proton. Yeah. I can erase with this thing. That shouldn't be. Basically, it's a proton and 2 electrons. So it's H. Forget it.
This would be better for you.
It would be called H minus. Well, yeah, but then I walked off the screen.
There's a blue one over there.
Yeah, that's the one I started with. It's dead.
Dead.
Well, and you've put it upside down, so it may work. Hydrogen, proton, plus 2 electrons going around. Going around. We know that electrons don't actually go around nuclei. But anyway, 2 electrons. So this is H minus.
What do they do, Dave? We've got a question from the audience.
Yeah?
What do the electrons do?
Oh, they're in what are called atomic orbitals, which are little fuzzballs of different sizes and shapes. And in this case, it's a little fuzzball. Looks like that. In this case, it's a fuzzball that has a core and a shell. In this case, it's a fuzzball that has a core, a shell, and another shell. That's if there's no angular momentum. If there is angular momentum, then you end up with dumbbell-shaped things and dumbbells and such.
Has this understanding changed since I was in high school in 1970?
Not in college. In high school, it may have, because high schools are always 10 and 20 years behind. People think that college level material, the kids are not ready for college level material in high school. They're wrong, but as long as they keep giving you information that's 20 years old, what can you do?
Answer is no. Among physicists, it has not changed.
No, that's not changed.
But you might have been
Dave?
taught the Bohr model in high school.
Yeah.
Are you saying that to have opacity, you have to destroy the photon? Or is it just
no.
if you scatter the photon, you're getting opacity also?
Opacity is anything that seems to transfer momentum to the gas. You've got a beam of light, it goes through the gas, and the gas seems to be nudged upwards by this upcoming beam,
Okay.
then that counts as opacity in our present context. In the case of the electron scattering, you could say, no, that's not opacity, you didn't destroy any photons. But these transitions clearly destroy photons. They get absorbed. After the transition, where's the photon? It's gone. And clearly then, 100% of the momentum of the photon was transferred to the atom. In this case, in some cases, a large amount of momentum was transferred, in some cases, hardly any, depending on the angle of the scattered photon as it exited.
So it's not opaque?
This counts as opacity in our present
Okay.
context,
Okay.
because it provides an upwards force on the gas. What happens with the hydrogen minus? Well, somewhere around, I've seen different numbers, 1 part in a billion maybe of the hydrogen at the surface of the sun has an extra electron, and so you call it a negative hydrogen ion. And you say, 1 part in a billion? Why are you talking about it? Well, I'm talking about it because that's where sunlight comes from. Almost all of the photons that come onto the Earth from the sun were emitted by negative hydrogen ions.
As those
Strange.
electrons fall back in or
Yeah.
leap away?
What happens is you've got a regular neutral hydrogen here, a proton, and an electron. Now an oncoming electron here gets captured by the hydrogen and emits a photon. And that's what's responsible for the continuum light that you see if you point a spectroscope at the sun. Yeah.
I was thinking that stars emit by black body type radiation.
They do.
So,
But in detail, where does that black body radiation come from? The answer is most of it, almost all of it, comes from this process. An electron gets captured by hydrogen, becomes a H minus, and a photon goes out. And the reverse also happens. Photons coming from below, most of them are coming from below, and there's a photon coming up. And then this electron is, let's say this electron here is knocked out of the system.
so is there something analogous to that to any black body radiator? Because like if you have a hot iron, it's
Yeah.
quite hot.
The details are different for each material. But in the case of the sun, it turns out that almost all of the continuum radiation that's not in spectral lines, almost all the continuum radiation comes from this process of ordinary hydrogen being transformed into H minus back into ordinary hydrogen. And this is an active enough process that, believe it or not, most of the light from the sun is coming from that process.
So that's not
In other words, if
at a
that,
particular frequency.
if you could wave a magic wand and make that process stop, then the photosphere of the sun would suddenly be deeper down, because this process would suddenly become transparent.
But wouldn't that emit at a particular spectral line?
No, because this is bound free transition. It's like this one here, where I had a electron there and it was knocked up into that up there. That's not at a line. That's not in an energy state of an atom. So this is a continuous thing. You could go there, could go there, could go there. Anything, any position that's higher energy than that. That's
So-
a bound-free transition, and that will produce a continuum of light in the spectrogram.
So Dave, before we get into meteorites
Yeah.
just vaporizing
Yeah,
and nuclear bomb analogies,
yeah.
are there any, I guess, examples of stars that we can observe that are especially noted for their opacity or?
Yeah, brown dwarfs and red dwarfs, and any quote late spectral types, anything that shows absorption bands. The more lines you've got, the more in the spectrum, the more opaque the material is, basically. Let me draw a little diagram, first of all, so that you can sort of understand.
It's 9:15.
I understand. We're doing okay. The units of opacity is centimeters squared per gram. I don't know if you can read that, but it says centimeters squared per gram. I looked at that. What kind of units is that? Centimeters squared per gram? And eventually I realized there's a way to think about these atoms that makes sense in terms of centimeters squared per gram. And that is, you draw a little parachute. Here is parachute. It doesn't want to let me draw it. There's a little square parachute. Has an area of 1 square centimeter. Here's some supporting lines. Down here is a mass. It has a mass of 1 gram. 1 centimeter squared, 1 gram. You say, what kind of diagram is that of an atom? Well, that's one that shows the cross-sectional area of the atom, how likely is it to get hit by a photon, and what's its mass. If you imagine that the whole sun is made up of these little parachutes with masses hanging from them, then you can understand opacity. It took me a while to realize that that was the at least the easiest way for me to think about the process. You got photons coming up here. Every time a photon hits this reflective surface, it gets bounced back, say. This is an oversimplification. It doesn't really get bounced back, but anyway. And here, so that's the interaction with the light. Here's the interaction with gravity, 1 gram, pulling downwards always. And you can see if the light gets really bright, this little parachute is going to accelerate upwards. If the light gets turned off, the thing starts to fall downwards. It's very strange.
Let's get into something else falling downwards.
Yes.
That's a little easier
Let's
for a
do
lot of us
a-
to get our heads around.
Let's do air friction vaporizing a meteor. Everybody knows that, right?
Mm-hmm.
Well, turns out it's wrong. Meteors do vaporize, but it's not because of air friction. There is a little bit of air friction when the airflow around the meteor goes around the side of the meteor. But what really happens is meteor is coming along like this. Here's the meteor. And the material in front of it can't get out of the way. This is going way, way, way faster than the velocity of sound. There's a shock wave here. Material is piled up here, lots of air molecules there. Out here is only a few air molecules. And this velocity is like 20 kilometers per second, 30 kilometers per second, something like that. If you do the math, you figure out, okay, we've got gas molecules with energy, kinetic energy of 0, and now suddenly they get hit by something that's going 20 or 30 kilometers per second. If all of that kinetic energy, if we transfer our thinking from this being stationary and that moving fast, make the meteorite stationary and have the airflow moving fast, this way, you can't make arrows, then what happens when you transform all that kinetic energy into thermal energy? You come up with an incredible number. You come up with a temperature of a couple million degrees. And when I first did that calculation, there's something wrong with that. Well, I kept doing it, and I kept getting a couple million degrees. So if all of the energy, all this kinetic energy, was transformed into heat there, all of it, then this material here would really be at 2 million degrees. In practice, no. Why not? Two main reasons. One is radiational cooling. Lots of photons coming out from that. This is a tiny fireball. That's what you see when you see a meteor. You don't see the object here. You see this tiny fireball in front of it. And the shock wave comes back like this. A rather steep shock because the Mach number is really large. And the other thing that happens that means that this couple of million degrees number is nonsense is that at any given time, there's much more mass in the meteoroid, now called a meteor, much more mass in that than this tiny bit of fluff which is the compressed air. So the couple million degree number is not entirely valid. There's a lot of energy left in the radiational cooling, photons coming out in all directions. Also, this meteoroid is getting heated, partly by hot molecules hitting the front surface, and partly, I think mainly, from radiation from this hot fireball hitting the surface. And I've seen numbers of like 20 to 30,000 degrees Kelvin quoted for the temperature of this material in front of the meteor. And that sort of intuitively seems, I'm comfortable with those numbers, 20, 30,000 degrees. I'm not comfortable with 2 million degrees. That's counterintuitive to me.
So are you saying we're
Yeah.
seeing radiation from the meteor or from the hot air in front of the meteor?
Mostly from the hot air in front, I think. But you often see trails coming back. And I'm not sure where that radiation is coming from. Coming from excited atoms, excited molecules, I suppose. Maybe little bits of dust that were knocked off of the meteor and are decelerating faster than the rest of the meteor.
But you still, I mean, I've seen meteors where you've got smoke trails coming off.
Yeah.
So there is still, something is being burned up.
The standard explanation I've seen is, oh, that's things like energized molecules. I don't know specifically what the chemistry is supposed to be, but energized molecules that are like phosphorescence kind of deal. I don't know. There are high altitude meteorologists who will be able to tell you what they think is responsible for that emission of light.
How does this differ? I mean, there's obviously a difference in speed, but compared to like when the shuttle used to come back in or a satellite comes back to atmosphere, I mean, it's a difference in speed, of
It's
course.
considerably faster than the shuttle.
Well, I know it'd be a lot faster, but
Yeah.
would it be something on, a similar, similar result, just at a different scale, or is it a whole different process going on?
I think it's similar. Yeah, it's similar.
So what's heating the space shuttle or heating the meteor, I think you're saying, is not the air friction rubbing on it,
No.
it's radiation from the compressed hot air.
Mostly radiation
heating
plus impact of hot atoms onto the surface.
That's air friction.
No, air friction is around the side here. Around the side, essentially nothing's happening. I mean, this is, a molecule here is much more likely to hit the front surface than to barely graze the side.
Why isn't hitting the front surface air friction?
It's not what I think of as air friction. Like if a car crashes into a bridge abutment, you call that friction? No, you call it a crashed car. Yeah. Friction is when your tire goes flat and your rim is grinding against the pavement. That's friction. But if you hit a bridge abutment, that's not friction. You see what I'm saying?
It's extreme friction.
I guess so. I can tell from my own experience. I've never tried it.
Just jumping
Yeah.
and going to dark matter,
Dark
and you
matter.
have an object you want to accelerate near the speed of light.
Yes.
Then if you have dark matter, you may get a similar impact type of situation.
It's hard to have an impact onto a black hole.
No,
So
I'm
you're
talking,
about
I'm
black
talking,
hole?
I'm not talking about black holes.
Oh, okay.
I'm talking about when they say, 70% or whatever
Oh,
percentage they give
okay.
of dark matter throughout the universe.
Yeah.
But it is supposedly matter.
Yeah.
Well,
yeah.
So let's say
Sorry,
you
I
accelerate,
went off camera.
so if you accelerate let's say you want to accelerate a vehicle at the speed of light,
Yeah.
besides running into the mass that increases,
Yeah.
you may run into dark matter as an inhibitor to reach-
Interesting thought. It's I-
That just makes sense though, because the only way we can observe dark matter is in large clumps that gravitationally
Could
deflect
be.
light. So
Could
that's actually a really interesting observation.
my own concept of dark matter would be, it doesn't matter how fast you go or how relativistic you get. I think the dark matter is still going to be inert. You're not going to. You'll pass right through the dark matter and not detect it.
And if it's tiny, like,
For example,
it could pass right through you.
the classic case of dark matter is neutrinos.
Okay, so they'd be
And
going right through you.
Billions of neutrinos
Yeah.
are going through your body all the
Yeah.
time.
Trillions.
And at close to the speed of light, maybe at the speed of light if they have no mass. And we don't detect it. It
Yeah.
doesn't hit us. So yeah. So this is maybe 20,000 degrees Kelvin. The comparison to the nuclear fireball is the initial newly formed fireball in like a hydrogen bomb or fission bomb is 80,000 degrees Kelvin. Only four times hotter. But surface brightness, assuming that it's reasonably opaque, you can talk about surface brightness if it's optically thick. Surface brightness is 4 to the 4th power greater. So the fireball, the new fireball, which only lasts for a fraction of a second because it's expanding rapidly and cooling rapidly, it's 4 to the 4th power, which is 256 times brighter surface brightness than this one. Of course, nobody can see this. It's a tiny dot. Nobody's been able to get an image of this thing. But if you could get an image of it, you would see that it's 1/256th as bright as the newly formed nuclear fireball from a weapons test. We're running out of time. We still haven't even done evening meteors cannot catch up to the Earth.
You can cut to the chase, yes or no?
Bottom line is, every meteor can catch up to the Earth because every meteor has a velocity at 1 astronomical unit from the sun greater than the Earth's velocity. Why? Because they're pieces of comets. A meteoroid that could not catch up to the Earth from behind would have to be near its aphelion. That would have to come from a comet which has an aphelion at the Earth's orbit. There are no such comets that I know of. So every meteoroid that encounters the Earth is going fast enough to catch the Earth, even from right behind. Yeah.
It's possible that the Tunguska comet was orbiting with alien and.
In such a very small orbit, somebody knows, but I don't.
That was more of a joke than.
You could look it up. You know, get on the web and find out what is said about by believable sources. What is said about? I mean, you know, Tunguska was really from the space aliens. You know, you don't really believe that. Anyway.
Aliens or no aliens, so what's the 30-second version of why we should be looking for meteors after midnight?
Oh, yeah, because they're brighter. When you do the math, you find out that it's with realistic numbers. You have to pick a velocity for the meteor, then you have to have a head-on collision, then you have to have a catch-up collision. The catch-up ones have 1/100th as much kinetic energy per gram as the head-on ones. A factor of 100, and it came out to 99 point something. You'd swear that I, fudged the numbers in order to get it to come out to 100. But where is that number? Anyway, here we go. 99.84. I just picked a number, 40, and then did the math. I came out with 99.84. So the head-on meteors are 99.84 times the kinetic energy. Well, there's two numbers you got to multiply together. One is the kinetic energy ratio, and the other is how quickly is the kinetic energy released. We multiply those two numbers because the ones head-on are moving very fast, and so they release their energy very fast. Ones coming from behind are moving slow, so the kinetic energy is released slowly.
Isn't it so that after midnight, the Earth is actually turned into the swarm in case of periodic...
Oh, you're talking about the rotational velocity of the Earth? That's entirely negligible.
Negligible? Not even when they turn into the orbit?
Yeah, no, it's totally negligible.
Okay.
We're talking about 1 kilometer per second
Really? Okay.
versus 30 kilometers per second, and you got to square that number to get energy. So you're talking about 1 versus 900. So forget, the Earth is stationary. It does not rotate, for these purposes. So, okay, so your head-on meteors typically might be a 2nd magnitude meteor. Your catch-up meteors are typically 7th magnitude meteors. And they're spread out in time by a factor of 7 to 1. Or the number I got was 6.8 or something like that. Which means that you got a choice. You can watch 7th magnitude meteors for 68 minutes, or you can watch 2nd magnitude meteors and see the same number of them, but 2nd magnitude instead of 7th. In 10 minutes. Choice to you. So, yeah, clearly you want to observe after midnight.
Good
So
advice
that was
from
a
Percy
quick run
for you.
through. I did do 3 of them. How about that? But I didn't have time to give you all the math for the after midnight.
Well, any additional questions?
Oh,
Okay.
For those who have not, I'm applauding your questions. For those of you who haven't heard about Bailey's laws, I'm Dave Bailey, so there's Bailey's laws. Bailey's first law says I can answer any question about astronomy, and Bailey's second law says I do not guarantee that the answer is right. So I'd love to get questions, and I'd love to comment on them, and I'm willing to go out on a limb if I don't have a solid answer.